Good morning. So today we'll continue with what we started last Monday. Sorry, like a couple days back. So we did a bit about CNN architectures. So before that, we talked about some layers: convolution layer, pooling layer, fully connected layer. And a couple of days back, we started with the architectures themselves. The first one that we saw was AlexNet. And I'm bringing back the slide because last time I had my iPad open and I don't know if I explained how well I was able to show Dropbox. Let me find my cursor here. Okay, it's here. So just to recap, did I say Dropbox? Dropout. What dropout is essentially is just going through the network and randomly deleting a few neurons in a particular layer. So in this case, let's say I am saying that I will randomly delete 2 or 3 neurons in a particular epoch. The red region is basically the ones that I'm selecting randomly in this third layer. And the goal is to remove these neurons from that epoch. So every single weight that is connected to this neuron is not going to be used for that particular epoch. And again, the goal here is some kind of a regularization framework. The best way I am able to understand it, for instance, is to say that it is removing this dependence on a certain neuron, so that what is happening is that you're not just you're basically learning. You're not just memorizing a particular path. Because remember, when we talked about like one of the biggest data sets out there, which is ImageNet, there's about 1 million images to train with. But the total number of parameters within AlexNet is like 68 million parameters. So there is a path within AlexNet that a particular image can memorize. So it can say that, it can start with this path here. I hope you can follow my cursor. So this, the activation from this neuron up top is going to be the maximum, let's say, and the activation from this middle neuron here is going to be the next highest, and that will give rise to the highest activation in the last layer up top here. So it can memorize this path and say that based on the path I have chosen, my output needs to be class 1 over here. And by using this kind of a dropout framework, we can minimize this memorization. We can say that in a particular epoch, this particular neuron is going to be deleted. So in essence, what is happening is that the connection or the path between the image and the class is broken. Your network has to learn something else or learn some other path within your neural network in order to now say that it belongs to class 1 rather than any other class. So the best way to kind of understand what dropout is as this kind of a regularization framework where you're making sure that memorization is not happening. The goal is learning, and memorization should not happen, right? And that is essentially what we saw here last time when we looked at the slide for dropout. Your test loss, your training loss increases quite a bit, your training loss decreases quite a bit and very easily, even until the last step or the last iteration or epoch over here. But there is a certain point in time, in this case it's around 8th epoch, where your test loss starts increasing, which is not what we want. Our goal is to perform well on the test data set, or on the validation data set, rather than on the trained data set. So we don't want to see this phenomenon. Rather, what we want to see is something like this blue line over here. This blue dotted line is with dropout, test loss, and you see that it kind of stabilizes after a while. That means that there is nothing more to learn for you from the data set that you have. So dropout is one of the best regularization techniques that we can use. And again, I'm saying that this is a regularization technique, but there are many interpretations of what dropout is. If you're into Bayesian neural networks and probability distribution, if you're coming from that community, then you probably will use this as an approximation for something like a Bayesian neural network. And these things are true across many kinds of methodologies. So I just wanted to bring this one slide back, since last time I was not able to show this on my iPad. So that was from the previous lecture. Now let's move on to the next lecture. So this basically continues from where we left off last time. So we looked at the locally connected layers, convolution layers, all the different layers required for CNNs, and then examples. We looked at 2 of them, which is LeNet architecture and the AlexNet architecture. There's 3 more pivotal architectures: VGG, InceptionNet, and ResNets, that we will look at in this class. And that is going to bring us towards 2015. Since then, there have been a few other things that have happened, transformer architectures, but those we look at once we do the sequence modeling part, hopefully somewhere in the middle of April. Same thing with diffusion models as well after we do autoencoders. So again, bringing back the slide, the history of CNNs, we moved from 1998, which was LeNet last time, across to like 2012, which was AlexNet. This is again the legend that we will be using. Anything with respect to conv layers is going to be in this kind of a block. Pooling layers, concatenation, dense layers, which we call fully connected layers, and some kind of activation functions, ReLU or Tanish functions. Batch normalization is not something we have seen. We saw something called LRN last time, which is a more local way of normalizing it, but batch normalization is something that we'll see when we come to GoogleNet. Then softmax layer. The repeated blocks are also quite important because we'll see this quite a bit. So whenever you see this kind of a square bracket multiplied by 2 or 3 times, that means that anything within the square bracket is going to be repeated that number of times. All right, with that, let's come to VGG architecture. So VGG was proposed by this group called Visual Geometry Group, and hence the name VGG. There are multiple variations of a particular architecture. So when VGG first came out, it was a VGG 16 or a VGG 19 kind of an architecture. But then when you look at the GitHub for VGG architecture, they have a VGG 29 and a 26 architecture. You'll see this in PyTorch as well if you were to load their models. So take this kind of an architecture with a grain of salt, which means that it's not the only architecture out there for something like VGG. There's multiple variations of this architecture. So in this class, we're just going to discuss about the most important parts of what this architecture was. And the most important part is that they designed a deeper model compared to AlexNet to show the efficacy of this depth. So we looked at AlexNet and we thought, okay, this was an extremely deep architecture with 68 million parameters. VGG was able to top that by more than double that amount in order to make their architecture. So the way they did it, the way they were able to go deeper was by grouping multiple convolution layers with smaller kernel sizes instead of having one conv layer with a larger kernel size. This is more easily explained in this slide. So there's a lot of stuff going on in this slide. Let's just concentrate on 2 of these here. The first one is AlexNet, and the second one here is VGG 16. So AlexNet architecture, you can see, has something called conv 1196. So conv 11 essentially means that the kernel size that the AlexNet has used is 11 cross 11. We saw before, right, the convolutional architecture, the idea of convolution layers and convolution itself. The kernel size of those weights were taken as 11 cross 11. And that adds quite a few number of parameters within this entire framework. By having this kind of a larger number of, larger size of the kernels themselves. And 96 here refers to the number of channels, number of kernels that is being used within a particular layer. So you can see this. So it starts off with something like conv 11, then there's a conv 5, then there's a conv 3, and max pooling layers in between before we finally go to this kind of a fully connected layer, and then your output. In all these cases, we are discussing from ImageNet dataset, which implies that the final output is going to be 1000 cross 1, or the number of classes you're looking at is 1000. And the size of the image is around 224 cross 224. And 3 refers to RGB channels. So these are the size of the image. So the same size is used across different architectures, but you can see the difference in the layers themselves in terms of kernels. The major difference between VGG 16 and AlexNet is the size of these kernels. So conv 11, you don't see any conv 11s within VGG 16 architecture, right? It's all conv 3s through and through. The difference is that they did not just have one kind of a conv 11 within the framework. There was a conv 3 and another conv 3 stacked one on top of the other before we came to this kind of a max pooling layer. The goal, so there's only 3 cross 3 convolution stride 1, pad 1, and 2 cross 2 max pool stride 2 layers within your VGG 16 architecture. So it's deeper using smaller filters. So the reason that these kind of smaller filters work is that the receptive field is going to be the same when you have a more deeper architecture. We saw this a couple of lectures back of something called receptive field. The goal is to look at the entire image. But we cannot look at the entire image in a single layer because the number of parameters required to do so is extremely large and it's computationally intractable. So what we do is stack layers one on top of the other. We take a convolution kernel, make sure that it goes around. We make sure it goes around the image, process that image, and we get a certain output. Then we put another convolution layer on top of these activations, which basically means that it's taking in the responses from all parts of the image that the first convolution layer has seen. Hence, the receptive field of your second layer is going to be greater than the first layer because you're just looking at a larger portion of the image. Now, the way you can increase the size of receptive field is either increasing the size of the convolution kernel itself, which is done in AlexNet with conv11, or you can stack one on top of the other, which is what is done in VGG16. So this allows VGG16 to have the same receptive field as AlexNet, but instead of having these conv11, 11 cross 11 kernels, it does it by stacking 3 cross 3 kernels one on top of the other. And again, the benefit of stacking, not just receptive field, but the fact that we are able to have this kind of a non-linearity added in between everything. So instead of just a convolution being a linear operator on the image, you have multiple kernels, all of which are acting on top of the image with the same receptive field, but now you have a non-linearity added to it. So this helps with the overall processing of the data itself. So in terms of the numbers itself, the AlexNet architecture, which had 16.4% of error rate, now decreased. In VGG16 architecture, had about 7.3% error rate. Again, we are looking at the top 5 error. So essentially, we are taking predictions of the top 5 predictions and saying that the ground truth belongs to these top 5 predictions. If it does, then we are increased. Then that means the accuracy has increased. This is the same thing, similar to what we had seen last time. So the pros of VGG architectures is, of course, that it's a simple design. It's simpler than AlexNet in terms of the size of the convolution kernels itself that is being used. Of course, there's an improvement in accuracy and more layers with smaller kernels. It increases the non-linearity. As I mentioned, we have 3 convolution kernels stacked one on top of the other, and there's always a nonlinearity and activation function between these kernels. So there is lower computational complexity because of the presence of these smaller kernels as compared to AlexNet, but the number of parameters themselves is now doubled. So AlexNet was around 65 million parameters. Right now, VGG architecture is about 138 million parameters. And again, parameters, what I mean by parameters is the weights and biases. Anything that can be learned during the gradient descent or the training process itself is what we're going to call as these kind of parameters. So we talked about this vanishing gradient problem before, and the way AlexNet solved it is by removing the sigmoid and the tanish activation function and replacing it with something like ReLU, which is a rectified linear unit. But at this point, now we have doubled the number of parameters. So, and it's gone deeper, right? If I go back to this slide, VGG architectures are much deeper than AlexNet. So AlexNet is this architecture, but this is VGG16. And on the right-hand side is VGG19, which is even bigger than VGG16. And then there's something called VGG26 and 29 architectures as well, which is even bigger than this. So essentially what we have done is the vanishing gradient problem has come back in again in these kind of larger architectures by increasing the depth further and further. So it does suffer from the vanishing gradient problem, and it's slower than ResNet. Maybe this doesn't make sense here. We'll talk about ResNet architecture in a couple more slides. But the next 2 architectures will try to rectify these 2 problems. The first one being GoogleNet, which rectifies the 138 million parameters, and the next one is ResNet, which overcomes this kind of a vanishing gradient problem. Any questions about VGG architecture itself? Yes.
Why do we take the value or the signal function after each calculation?
Can you repeat that?
Why do we take the value or the function after each calculation?
Why do we take nonlinear activation after every convolution? So convolution is a linear operator, and we saw this back in lecture number 5 or something like that, where a single layer, if it's a linear operator, all it is doing is constructing a linear classifier between the data that exists. But if your data is non-separable to start with, a linear classifier will not help you. This is where you would need to go to a different kernel space, for instance. And that kernel space, one way of thinking about that kernel space is some non-linearity that has been applied on your data in order to move it to a different spot, right? So think of that kernel or that nonlinearity right now, not just in the initial data space, but in this representation space as well. So if I call this, let's say somewhere here as the representation space, at this point, a simple convolution layer, all it does is create a linear classifier or a linear line. But by applying this kind of a nonlinearity, you're moving into a space that becomes separable, hopefully. By the time you come to the very end, by the way, this is just a simple fully connected layer, which implies that it is this kind of a classifier. So after doing all these kind of nonlinearities and convolution, you come to a space where your initially non-separable data is now separable. So that's the whole point of adding that nonlinearity, is moving from one space to the other one in order to come to a space which is your data is separable. So FC is basically the same size. This is going to be a different size. So this is 4096 cross 4096, 4096 cross this thing, and FC2 is essentially, I believe it'll be a 4096 cross 1000 cross 1000. So it's just the difference in the sizes. When we saw this kind of a PyTorch example last time, we had defined FC1 in the init framework. We had designed the FC1 and FC2 separately, and then in the forward function we had applied that FC1 and FC2, right? So this is just going through that kind of terminology. It still is a fully connected layer. All three are still fully connected layers. It's just the dimensions are different. All right, so the next architecture is something called Inception Net architecture, or in the beginning when it first came out, it was called Google Net architecture because the authors were from Google. The novelty of this architecture was something called a network-in-network model approach via something called inception modules. We'll talk about what those inception modules are, but essentially it's looking at a hierarchical representation of your data with different size kernels. The most important part in GoogleNet is this idea of batch normalization. We talked about LRN normalization last time, but this time we're going to be talking about a learnable way of normalization, which is going to be about batch normalization. So it reduces the computational cost without affecting generalization. This word generalization essentially means that you are doing well on your test data. For now, let's just think of it as, given a training distribution, we have a test distribution. The goal is that we are going to learn something from the training distribution in order to test on the distribution that we are given, which is our testing or a validation distribution. Generalization essentially means that given any kind of a test distribution, we should be able to manage our goals. So let's just think of this as some kind of a test loss currently that is going to help, or we are doing well in terms of the test accuracy itself. So it also used something called global average pooling at the last layer instead of a fully connected layer. So until this point, whenever we talked about pooling, we talked about one important part, which is the max pooling layer. The goal in max pooling is the invariance to existence of features. If your features exist in different parts of your image, your goal is to make sure that your network, it doesn't matter where the locality of these features are, your network recognizes them and uses them in a classification framework. So that is, max pooling helps us quite a bit with that, with that condition. Global average pooling, on the other hand, we also saw this when we looked at the pooling layers. All it's doing is taking an average of the kernels rather than the maximum value. So instead of doing a fully connected layer, which is just multiplying your weights with your activations and adding a bias, it's just taking an average of all your the final layer outputs instead of doing these kind of multiplications and additions. That's another difference that GoogleNet or InceptionNet did. So let's discuss about the most important part here, which is the InceptionNet, Inception module itself. So till now we were looking at architectures where it was this kind of a sequential architecture where given a large image, let's say 224 cross 224, we had these 3 cross 3 kernel that acted on top of the image. Then there was a 3 cross 3 kernel that acted on top of the activations of the previous 3 cross 3 kernel, right? It's stacked one on top of the other. Inception module kind of did not use that hierarchical representation. Rather, what it did is given an image here on the left-hand side, a 224 cross 224 image, it performed a convolution 5 cross 5, 3 cross 3, and a 1 cross 1 module, all of them on top of the image directly. And then, of course, you have the ReLU architecture, your ReLU activation function. So essentially what it did is it looked at kernels of different sizes. So if you go back to AlexNet, if you have this kernel of 11 cross 11, then it's looking at the size, what it's convolving on the image is a size 11 cross 11. So you'll have some kind of a structure within that 11 cross 11. We lose that completely when we do 3 cross 3 images. This is going to become more clearer when we visualize the network itself and the filters. But essentially, you have lost that hierarchical representation when you move down to the 3 cross 3. What Inception module does is on the same image, it applies a 5 cross 5 kernel, a 3 cross 3 kernel, and a 1 cross 1 kernel in order to get the outputs. And finally, it just concatenates everything into a single vector. So what you have here is a multi-layer representation, a multi-scale representation of your image. And before this, when we were doing like traditional signal processing and image processing algorithms on top of images in order to identify or recognize, this was a very famous trick, this idea of a multi-scale framework. We used to take an image, let's say it started off being a 200 cross 200, then we processed it as a 200 cross 200 image. Then we downsampled it. We downsampled it to 150 cross 150, processed it, downsampled it to 100 cross 100, sampled it, processed it, and so on. So this kind of a multi-scale approach was very, very common when it came to like signal processing and image processing methodologies, which was not there in deep learning because we had this stacking sequential thing when we were more interested in the receptive field. But Inception module turned it over its head where it said that, okay, let's have multiple kernels that does 5 cross 5, 3 cross 3, and 1 cross 1 on top of the image for us to get our output. So this idea of spatial information at different scales was preserved in InceptionNet. Question, yes?
What's the meaning of a 1 cross 1 convolution?
It's the same thing that we had discussed before, which is it's looking at a particular input as if, I'm sorry. Yeah, by one number, exactly. But before, what we had was that 1 cross 64 that we talked about last time, which is the number of kernels. That doesn't exist at this point. It's just a 1 cross 1 kernel, but it's just a multiplication of everything. So give me a second. So, all right. So the next important part within InceptionNet architecture is the idea of batch normalization. So when we did the local response normalization last time, it was a little bit different than what we are used to in terms of normalization itself. All it was doing is it was looking at the kernels and doing this formula A divided by K plus alpha into the sum of squares of all the kernel outputs, right? So that is a good way of normalization, but the problem with something like that in LRN, in AlexNet, is that it's not controllable via backpropagation. There's nothing to learn within the framework, within the backpropagation process itself. So it's something that we define in the beginning and leave it as is. So K, alpha, beta were all hyperparameters that we had to choose to begin with, and it was very hard to continue doing this for much larger architectures. So batch normalization was introduced where the goal is, and this is probably more similar to what you are used to in terms of doing normalization. Maybe if I move to the next slide here. Instead of looking at each element's corresponding outputs in the kernels, batch normalization did a very simple thing that we do on data. Normalization that we usually do is we take a kernel, we subtract it based on the mean, and just divide it based on the variance, right? This is what we do in terms of the data normalization itself. Batch normalization does this across different layers. So as soon as, let's say, a con3 layer is done, it looks at all the activations, all the outputs from your activation functions. It uses that and it creates this kind of a mean set of kernels. So again, just going back and talking about these images themselves. So every block that you see over here is essentially one kernel. So there are three kernels essentially, which is depth-wise. This, hope you see my cursor here. This here is one kernel. The next one, you see the top and the right part of the kernel. And the last one, the top and right part of the kernel as well. So these kernels that are stacked on top of each other, based on all the other channels that may exist, you can create a mean set of activations, and then you can get the variance of those activations as well. So you'll get the same size of the kernels, and once you subtract and you divide, this essentially is batch normalization. We are not doing it just for, let's say, a particular output correspondingly, but rather the entire thing. The problem with doing corresponding activation normalization that we did in LRN, in AlexNet, is that it doesn't always need to match. Your corresponding kernel here does not always need to match whatever the corresponding kernel was in the second set of kernels in your convolution layer. But by imposing LRN, you're making sure that they try to match. So you're adding a different layer of complexity to your training algorithm, which again is not controllable. So it's something that you start off, you define alpha, beta parameters, but you never have control within the process, the training process itself. Batch normalization, on the other hand, you have yi is equal to gamma xi cap plus beta. So these numbers, the gamma and beta, are learned during the optimization process itself. So what I mean by this during the optimization process itself is in VGG, in AlexNet, when we had 65 million parameters, it did not include the alpha, beta, and k parameters. It's something that we learned. But in batch normalization, when we talk about the number of parameters in GoogleNet, gamma and beta are part of it. It's something that we are learning across the training process. So normalize the entire batch B. This is important as well. So we are usually in deep learning, the way we do is we do the mini batch kind of optimization framework, where given a large amount of data, where let's say 1 million from ImageNet, it's not possible to train this entire, using the entire batch of gradients. So we use some mini batches. So the UB and sigma B, which are the mean and the variance, are taken across this particular batch. So we, during training, let's say 1,000 is my batch size. I pass it through the network. At some fifth layer, conv layer, I'm going to take the output of my activations. I'm going to take the mean, the variance, and use this formula here to calculate your xi cap, and then yi, which is gamma xi cap plus beta. So again, the most important part here are these two trainable parameters, gamma and beta, which does the scale variable and the shift variable to scale and shift the normalized mini batch outputs. So this gives like a difference between LRN, the local response normalization we saw last time, which was in AlexNet, versus batch normalization. There's something called internal covariance shift, which is essentially what it does. So I drew this last time when we had this kind of a Gaussian distribution. I'm not using my iPad, so I can't draw right now, but essentially if you had some kind of a Gaussian distribution with a different, I don't know, like let's say 2D Gaussian distribution, covariance matrix is something like 2, 3, 5, and 7. So this is not a perfect round sphere, right? It's basically some kind of a shifted, scaled oval. We want to make sure that particular covariance matrix is, let's say, maintained across the different layers. But usually when we do these convolution processes, it's not maintained. So that is essentially what we call internal covariance shift. Internal, because within a neural network, within the architecture itself, your covariance of your data keeps on changing across different layers, and that's the shift that happens. We want to make sure that the internal covariance shift is reduced as much as possible, and by doing this kind of a normalization, we tend to decrease the amount of internal covariate shift that can happen. It's trainable because gamma and beta are parameters that are trainable parameters. So we normalize the entire badge and shift the mean and scale the variance using these two hyperparameters, which are gamma and beta. So the good thing about GoogleNet or InceptionNet v1, as it was called at the time, is that the number of parameters have now decreased quite a bit. From 138 million parameters that was there in VGG architecture, we have now reduced it to just 4 million parameters. So the cons, however, is the last one here is very important, which is the representation bottleneck reduces the feature space in the next layer and leads to loss of useful information. So while GoogleNet and InceptionNet v1 is very good on ImageNet task itself, it does not do well when we transfer it to a different task. So even today, VGG16 is an excellent architecture where even though it performs very well in the image classification itself, I can then use this architecture in different applications. I could use something like visual question answering, and it does quite well in those kind of applications when I train it. But GoogleNet does not. The performance is very tuned to this idea of image classification because, again, the idea of this multi-scale representation comes from image processing community. It is very, very tuned to just one particular topic, which is classification of images. But when you move to a different kind of an application, let's say video processing or visual question answering, it does not do as well. The generalization capability is not as much because after every single layer, there's a lot more information that is lost within this architecture. So with that, we come to ResNet in 2015. So probably the most famous architecture or the most pivotal architecture that exists. Even today in all research papers, ResNet is probably the, whenever there's images or videos involved, ResNet is probably your go-to architecture in terms of training and testing. It's an accepted architecture. If you write a paper if you write a paper about something where it uses ResNet, it's accepted from the community and the reviewers themselves. If you do something on AlexNet, let's say, then you might not get your paper accepted in some of the major ML conferences because it's considered a bit old right now. But ResNet is still one of the best. And one of the main reasons for that is this thing here, which is ResNet was the first architecture which beat human performance on ImageNet dataset. So let's talk about what that means, essentially. So we saw ImageNet last time was about 1.2 million images with about 150,000 test images, right? So if I take the 150,000 test images and show all of you, then it's not, most of the time, it's not very obvious what this image belongs to because, again, ImageNet has 1,000 different classes that a particular image can belong to, and some of these are very fine-grained, as I mentioned. The difference between something like dog breeds, a boxer and a bull mastiff, is very hard for most people to kind of differentiate between. So in a lot of cases, human beings themselves are uncertain what a particular class is, and they make mistakes themselves. And that mistakes is around 5%. The error rate in ImageNet is 5%. Again, this is the top 5 error rate. So that means that human beings were not able to look at an image and classify it in their top 5 predictions. They were asked, given an image, they were asked, tell me what your top 5 predictions of this image are, and the ground truth was not part of it. That's the 5% here. ResNet architecture was the first one that was able to beat the 5% human error rate. It went down to about 3.6%. So top 5 error in ILSF VRC 2015 challenge. This was lower than human recognition error. So one of the most important things that ResNet did was addition of something called residual blocks and something called skip connections. So usually, again, AlexNet, VGG, GoogleNet, everything had this sequential thing where X came in, you had weight layers in AlexNet and VGG, and in InceptionNet, you could think of it as a separate weight layer to the sides here as well. This was weight, let's say 3x3 versus another weight 5x5 and weight 1x1. That is how architectures were. The way residual networks work, or this idea of skip connections, is that your X is now directly skips the weight layer, and then adds itself to the outputs from those layers at a later stage. So that's why we call this as a skip connection. So X, let's say, was your input. It passes through your weight. It passes through another weight layer, ReLU. Let's call this entire thing as a block. Let's call it a residual block. So that will be f of x. So at the end, there's an f of x plus x. So the output of x directly comes in and adds itself to f of x before it goes to the ReLU. And this is something that is repeated across frameworks. So in this case, you have con block, you have an identity block. I don't know if I have that architecture. Maybe this is a good architecture to talk about, just to show what it looks like. So you have a ResNet 34, which is a 34 residual architecture. So your input image comes through. You have some kind of a convolution layer. Can I zoom this? Apparently not. So I don't know how visible it is, but the numbers don't matter. Essentially, what matters here is this idea of skip connections, where you are skipping these two conv layers, and the X is now being added directly to the output of these conv layers. Same thing again. You have another two conv layers. You're skipping again, and the output of the previous one moves to the next one, and so on. So what this does is so let's go back to the idea of why we are doing this. It's because of vanishing gradient problem. So we had a huge problem with vanishing gradients when we talked about LeNet in 1998. So till 2012, nothing happened. We were not able to construct bigger architectures because of vanishing gradient problems. AlexNet kind of solved it by adding a ReLU activation function, but then VGG took it to the next level by doubling the number of parameters, by doubling the number of layers, right? So what happened is right now we are back to square one, where we had a vanishing gradient problem. But by having these kind of skip networks, your gradient now doesn't have to flow back through every single layer to reach the first layer. So as I've mentioned before, backpropagation is a very greedy algorithm. It tries to use as much of the error as possible when it's doing the layer. So when it's doing its updating. So there's going to be a lot of error in the final layer, which means that these two layers are going to get a lot of error to update themselves. But when it comes to the very end over here, there's not as much to update. So this is the vanishing gradient problem, where the gradients in the first layer, really, it's not helping you a lot. Backpropagation is not helping you a lot. But by adding these skip connections, you are taking the error that you had at the very end, going back twice, and not moving through these kind of middle layers that can exist. Right? So these skip connections help you with the vanishing gradient problem, and that is the most important, one of the main reasons of having these kind of residual blocks and skip connections between residual blocks, where we could train these very, very large models. So if you look at ResNet, we have VGG that kind of tops off at VGG 29, but ResNet architectures has ResNet 18, 34, 50, 101, and ResNet 152. In other words, there are 152 layers that can exist within this ResNet 152 architecture. And that helped the architectures become, or it reduced the error rate even compared to humans as well. Again, residual architecture is one of the most important reasons for that. Yes?
Could you re-explain like how the error backpropagates with the skip connection?
So let's say the error here starts off with 1,000 or something like that. Backpropagation is a greedy algorithm, so the first layer here is going to use up 500 of that error in order to, let's say, update its own weights. Now the remaining 500 is going to be 250 of that is going to be used within this other weight layer over here. So by this time, you've lost about 750 of your error already. And by the time it's going to come to this particular spot, it's going to be very, very low. Something like 0.2 is the total layer for all the parameters that exist. So the way residual connections work, skip connections work, is this 1,000 error is going to be used in these two layers, and it's going to be used in the previous, and it's going to be backpropagated to this directly. So whatever error is, we talked about 500 here, 250 here. 250 is remaining, right? And then the 1,000 error from here is going to come back here again. And we are going to use that error in order to backpropagate and update our weights within the network. Again, the numbers themselves are very made up, but the idea, the motivation is something like that. Yes?
Is there a reason why the skip is 2?
It's usually something called like a residual block, And the way the paper defined this residual block is in this way. But since then, there have been many other architectures. It doesn't have to be two. You just have to define something called a block, a residual block, and whatever's inside, it's fine. You don't want to have too many blocks within that framework, because since you're skipping it, then that means that it might not have as much effect on your outputs. So you want to make sure that there's this balance, that you're skipping it, but the output of that also is important in your framework.
Is there like a trade-off between like how accurate it is depending on how many blocks you skip?
Yes. So in ResNet 152, for instance, the blocks themselves will be the same, but the number of blocks is going to be high. In ResNet 18, the same case. ResNet 18 compared to ResNet 34, the things within the block is going to remain the same, while the number of blocks is going to increase. So more number of blocks means that more amount of things that you're learning within them, it's going to be better. But if, let's say I had something like a ResNet 250 or something, you want to make sure then that we are doing a lot of skip connections and making sure vanishing gradient is moving away. But if you increase this to a very large number, you still will have that vanishing gradient problem. So you want to make sure that trade-offs, that you are learning something and gradients are helping you during your training process. So you want to make sure that the amount of blocks is limited. It doesn't increase to a very, very large number. Yeah. Yes?
Are skip connections only used in that application, or are they doing something in the forward direction?
It's in forward direction as well. Yeah.
How do you decide what goes through the skip connection and what goes through the weight?
Everything goes through the skip connection and everything goes through the weights themselves. Yeah. Again, there are different variants. So there are multiple papers that use the skip connections in different ways. So you will have some kind of a, let's say, like a weighted function between them. You can have something like a weighted function between different layers, and this something like an alpha plus 1 minus alpha into these things. So there's multiple ways of thinking about and using them separately. This is for this particular architecture. Sorry, from this paper itself. We're only talking about this one paper in from 2015 or 2016, which was like a pivotal paper. Yes? This one? This is the kernel size. So 3 cross 3 kernel, 64 is the number of channels. So we, 2 weeks back or 2 lectures back, when we discussed, you have your 5 cross 5 kernels, which is going through everything, but then you can have multiple 5 cross 5 kernels. The number of that multiple is the channels. Yeah, that's it. That's the 64 are all the number of channels. Yes. Can you repeat that? Oh, so yes, you have to pad. Essentially, there's a lot of padding that goes on between them in order to get the exact thing. Yes. I don't know for this paper how they have done it, but you usually pad it with zeros. But I have to check up on that. I'm not very sure about that answer. Yes.
Is it typical for new architectures to be published in papers so that the whole community can know how it works?
Not really. I mean, it depends on. So this particular architecture is like very, very large, right? If you can replicate the same performance in a smaller architecture, then that means it's a publishable paper. Even today, there's a number of papers that keep on getting published regarding architectures themselves. Like a couple years back, there was AffiliationNet, which using the same lesser number of parameters than AlexNet was able to get similar results as, let's say, ResNet. And there's something called MobileNet, which even with lesser number of parameters can be run on your cell phone. So there's a number of ways that you can claim novelty in order to make sure that it gets published. All right, so regarding the pros of ResNet, it greatly reduces training time and improves accuracy. Does not need to fire neurons in every epoch, and once a feature is learned, it focuses on learning new features. So the vanishing gradient problem that was experienced by VGG is now solved because of the existence of the skip connections within the network itself. Of course, there's a lot of cons, but we are only talking about these pivotal architectures. There are multiple other cons that exist. Like, for instance, it's a very, very large architecture. You cannot use it on, or you were not able to use it at the time on cell phones, and there had to be new kind of methodologies that would have had to crop up. Even today, when we discuss the, if you see papers, ResNet 152 is not always used. ResNet 18 and 34 are still very, very famous architectures that are almost always there in papers. But again, these days the connets have been replaced with transformer architectures, and we'll discuss about those in after a while. I believe the first transformer was in 2017, which was 1 year after these ResNets. All right. With that, we move to the next part, which is the training CNNs. And we'll go through this quite quickly because, again, the goal of this course is not about the math associated with the optimization, but to give you more of a motivation for these optimization techniques. It could be, every part of this could be its own lecture, essentially. It's similar to what we discussed during the regression portion of the course. So our goal is now to find these optimal parameters. Instead of having just one, a very small amount of W's and B's, we are now looking at millions of parameters, possibly billions with the newer architectures that exist. So our goal is to now to find the most ideal, the optimal parameters. And similar to before, gradient descent is our best bet in finding our results. So in ANNs, which was the multi-layer perceptrons, the weights and biases can be learned via backpropagation and gradient updates with the loss function. So the loss landscape of CNNs are non-convex with local minima. So whenever we discuss about gradient descent, we showed this very nice parabolic curve, and where the global minima was the local minima, and our goal was to move to that local minima in a stepwise fashion, and we were able to do it quite easily. In a stepwise fashion, we moved to the local minima. We saw that this local minima was the global minima. This is when the gradient was 0, and everything was easy and straightforward. The reason for that was the the manifold itself was convex. But what you see over here is that the loss landscape is usually not convex in CNNs. And there's a very simple way of thinking about why that is. Given like a very simple coordinate that we usually draw in terms of the fully connected layers, if you just move the first neuron to the second position, and then move the corresponding weights as well. If you just permute through all the neurons, you have different architectures, but the exact same loss. So essentially what you have is, if I do pen, your loss function is going to look something like this. So at every instance, this is a different architecture where you have permuted through your neurons and said that instead of the first neuron being where it is, if it were in the second neuron's position and the corresponding weights were moved, the loss would be exactly the same, because again, it's just a bunch of W and B that you're just adding together, multiplying, and then a non-linearity at the very end. You just add them all up in non-linearity, right? So so these would be considered different architectures when you move neuron 1 to neuron 2, but the loss would be exactly the same. So this is not a convex function. But still, we do use some kind of gradient descent algorithms in order to construct our best possible parameters, are what we would call optimal parameters. And of course, so your local minima is not your global minima, which is a very, very big problem. But then you have other issues in optimization as well, which is that noisy gradient estimation, many saddle points, and ill-conditioned loss surface. This is what we mean by ill-conditioned loss surface. Yes. Convex, you would say something like this, and concave would be something like this. So non-convex would be like a combination of all of them. Yeah, I don't think that's obvious at all. It's just the way we speak about it. Concave and convex have specific meanings from an optimization community. There's a lot more to that definition. I'm just putting it like a drawing thing, but there's a lot more to that definition. But when we say non-convex, it could be like a zigzag curve. It could be all these things. So simple gradient descent, this is a slide we have seen before. Given some kind of a loss manifold, we define a gradient as some kind of a tangent towards this loss manifold and move along that tangent and say that along this tangent would be the minimum loss that we could or we should be able to get. And the way we do gradient descent, again, we saw some of these slides are from the regression regression portion of the course. We have 3 ways of doing gradient descent: batch gradient descent, stochastic gradient descent, and mini batch gradient descent. We'll go through them quite quickly since we have already seen this before. Ideally, batch gradient is taking the entire data within your optimization framework in a single epoch. That means that if I have 1 million images in ImageNet, I'm using that to train. I'm using all my million images in a single epoch to find what the loss function is going to be. The difference from the last time we saw these particular slides is this thing here, where instead of doing the gradient yourself, if you were using PyTorch, you can just take wtensor.grad. So if you're using your W as your variable in order to create your function, and you have defined that you need a .grad function within it, then PyTorch automatically saves off all your gradients, and you will be able to get your gradient and B. You can use this entire thing. You can substitute with something called an optimizer.step within your gradient descent. Again, if you do a very simple exercise, it'll be there in the homework as well, but if you do a very simple exercise on MNIST dataset, you should see this particular command, which is an optimizer.step. So batch gradient descent takes all the million images in order to calculate your loss function, and you keep on doing this until you set yourself a criterion saying that if my loss function, if my gradients, are lesser than a particular threshold that we'll call as tolerance here, which is epsilon, then you can stop your gradient descent process. Then you say that your network has converged and you don't need to do the process or continue the process forward. Mini batch gradient descent, actually let me do stochastic gradient descent first because the other one is kind of halfway between them. Stochastic gradient descent essentially does it image-wise, or for a particular data point, you take what the loss function is, you update your algorithm. Next, you take the second data point, update your algorithm. Third data point, update your algorithm. You do it across 1 million images, keep on updating it 1 million times, and once you've done across all the images, then you have completed a single epoch. So now restart back, go back to the first image, update your algorithm. Second image, update your algorithm. Once you do it, you're done with second epoch. So it's a very, the number of steps or iterations is very, very large in this particular case in stochastic gradient descent. And every element is very noisy, and that's why you see this. If I go back to batch gradient descent, you'll see that it's almost always going towards the global minima. But when I do stochastic gradient descent, it's not. It's a very, very noisy process. But in many ways, it's very good for us. Since this is not a convex function, we want to make sure there's as much noise as possible within our gradients, that we are giving our a network a chance to move away from the local minima to go towards your global minima. So batch gradient descent is never used within these kind of large neural networks. Stochastic gradient descent, or SGD, is very, very famous, one of the more famous optimization techniques out there, at least until about 2017, 2018. This was the one that was always used. Any processing that is done in terms of, let's say, batch normalization or anything that we saw is done on these things called mini batches. So again, we still cannot take 1 million images in our batch, but if we choose, let's say, 1,000 images within our batch, we can use this as our normalization for our normalization framework. It's somewhere halfway between a full batch gradient descent and a stochastic gradient descent. You're choosing a smaller number of images, let's say 1,000, in order to do the optimization framework. Again, epoch is considered as the 1,000 multiplied by how many ever mini batches we have in order to make 1 million. So the word epoch is always when you look at all possible data points or all possible million images that you're using for your training framework. So generally the way we do, question? Yes, so it's, that's a good question, and there are different ways of doing it. So within your optimization framework itself, you can set this parameter up where you can randomly choose, and the usually the way we do it is randomly choose it. So you don't need to have a specific subset that will go through across the entire million images. Usually random is the best choice in most cases. We usually say that once it finishes the total number, you're done with the result. But again, in your optimization framework, you have those choices you can make. You can set flags saying that I want all my data points to be taken into consideration, or I want like balanced data points to be taken into consideration. So that means that within every mini batch, there's the same number of images of every particular class in your training set. So there are multiple choices that you can make in order to set that thing. But in general, the most simplest thing, just take a random subset. That will usually give you the answer. Yeah. All right, so in practice, we use a subset of the data, mini batch, at each gradient descent iteration to calculate the loss and estimate log gradients. So mini batch is something that is usually used in most frameworks. So the next part is the idea of this. Let's call this, there are many ways of talking about what this is. Loss surface, loss landscape, your loss manifold. But we'll just use the words loss surface right now in order to describe what our loss surface looks like. So it's not a very simple convex function. It's this combination of convex and concave functions across the entire trajectory that is possible for your algorithm. There's a lot of local minima. Usually in convex function, your local minima is the same as your global minima, but that is not true anymore in CNNs. And more importantly, there's something called saddle points, which you see here at the bottom. Saddle points are essentially where gradients is 0, but it's not your local minima or your local maxima. Take this case, for instance. At this point, or this point here. At this point, your output has 0 gradient. I hope you can see my cursor. Yeah, your output has 0 gradient when you do your loss function. But as you can see, at the bottom over here, it keeps on decreasing, right? So this tells you that your gradient descent algorithm is going to tell you that your loss is 0 and you're done. Your gradient descent process should end. But that is not the case, because it's clearly visible that on the left and the right-hand side, there is a loss function, or the amount of loss is going to be lesser. So using a simple gradient descent is going to fail in this setting. We need to use more different kinds of variations of gradient descent in order to find solutions when there are saddle points. We'll look at a few of these things. We'll try to complete as much as possible today. Remaining, we'll do it on Monday. But let's start with something called momentum. The idea of momentum is very simple. If you're going down a particular plane, then your current iteration in your gradient descent is only dependent on the current gradient and nothing beforehand. But momentum says it shouldn't be that way. Momentum says whatever gradient descent, whatever gradient or loss you were using in the previous iteration should influence your next iteration as well. And a simple intuition is, imagine a ball that is rolling down this loss surface. It has a certain momentum associated with it. We use that momentum in order to move through the local minima going towards the global minima. Maybe I start by showing you a demo. I think, let me find, yeah, this particular demo. So this is a non-convex loss surface, right? So there is a local minima at this particular point, and then there is a much bigger global minima at this point. So our goal is to move from wherever the two balls here start from towards going to the global minima. But sometimes what happens with gradient descent is that as soon as it reaches this kind of a local minima, it stops because it has reached your tolerance value. Your gradient, norm of your gradient is less than a particular epsilon, hence gradient descent will stop at this point. But what happens with momentum is that it passes through the local minima because of the fact that there is some velocity associated with it. It's not just a simple norm of the current gradient, but it's norm of the current gradient plus whatever gradient was before. So gradient at this point would be there. There would be a large amount of gradient. So it's not going to stop at this point. It's going to continue on towards a global minima. So this is like an intuition example of how to create of the difference between momentum and local minima. Sorry, momentum and gradient descent. It helps you in this kind of local minima and sort of saddle point. It doesn't stop at, let's say, saddle points. It keeps on moving because of the fact that the previous iterations had some gradient associated with it. From a mathematical perspective, the way we are doing it is in simple gradient descent, it was Wt plus 1 equals Wt minus alpha into dou L by dou W. That is how the simple gradient descent worked, right? Now we replace that with a function called v of t plus 1, and v of t plus 1 is a function of the current gradient, that is dou L by dou W, and the previous iteration of your v of t. So v of t plus 1 is whatever gradient that you have or the momentum that you have at this iteration, and the previous iteration is given by v of t, and there's some factor, beta, that you're adding or multiplying your result with. So v of t, we usually call it as a velocity of time t. Beta is some kind of coefficient, momentum coefficient. If it's 1, then essentially that means that we are weighing our previous iteration as much as our current iteration, which should not be the case. Ideally, this should be much lesser, or it should be less than 1. And then, of course, you have gradient at time t. When you have beta equals 0, then look at the first equation, v of t plus 1 equals 0 plus dou L by dou W. So if you just take v of t plus 1 equals dou L by dou W, that is nothing more than a gradient descent algorithm. So one mathematical way of thinking about what this v function is it's an exponential running average of gradients, because if you take the v of t and replace it with previous iterations v of t, so that means that it's beta v of t minus 1 plus dou L by dou W t minus 1, right? You can keep on doing this. V of t minus 1 can now be a v of t minus 2, and that multiplies itself with beta cube and so on. So that's why another reason why beta has to be less than 1. If beta is 1, then that means that v of t beta cube and v of t minus 1, v of t minus 2 is going to matter the same as the current iteration, which you don't want. If this is 0.99 or 0.9, for instance, beta square would be, if it's 0.9, then beta square would be something like 0.81, which would mean that it's 80% of what it was two iterations back. Beta cube would be, I don't know, 0.729, I believe, which would be 70% of what it was 3 times back, and so on. So you want to make sure that it's less than 1. We saw this before. Any questions in terms of what momentum is? Yes?
How do we prevent the gradient from continuously oscillating at the global?
So in this case, like here, for instance, right? So your learning rate alpha is your best bet to do here. So alpha is still what it was before, which is your alpha. So let's say you have learning rate. So let's say you have 200 epochs. The general way we do this is the first 60 epochs, it'll be 0.1. Next 60 epochs, it's 0.01. The next 60 will be 0.001, and so on. So as and when, so your hope is that by 100 epochs, you're near the global minima. And by decreasing this alpha quite a bit, that means that you're not oscillating as much. You're moving towards the center as much as possible. So alpha is your best bet if you don't want to move around the global minimum. Yes?
How do you initialize the velocity?
It's 0 to start with, but after that, it kind of adds itself, right? So v of t, let's say, is 0 in the beginning. The first iteration is nothing more than gradient descent. In the second iteration, you already have a v of t, which is your previous gradient. So it's the previous gradient multiplied with beta plus the present gradient. So you start with 0 as your simple initialization. All right. So another way of trying to understand this kind of optimization framework is by something called loss curvature and condition number. So again, this comes from a topological perspective. If you learn about topography in math, there's a lot of stuff that goes into trying to understand what this topography is. Convex function, it's very simple again, but for non-convex function like what we have with CNNs, it's a very large research field out there. The easiest thing that we can use to determine what this surface looks like is by using your Hessian matrix. Hessian matrix, as we had seen before, is delta square theta 1 square L of theta. So it's the second derivative of your loss function that can exist. But instead of looking at this entire matrix, it might not make too much sense to look at the entire matrix. We can use some kind of a number called a condition number in order to understand this surface. So for instance, the eigenvalues of this h of theta are the principal curvatures of the loss, and eigenvectors are the principal directions of curvature. Now, technically, this is the first time we are looking at the words eigenvalues and eigenvectors in the course, but specifically, it's very similar to the U and V that we saw in terms of the singular value decomposition before. The only difference, of course, is now we are looking at a symmetric matrix that we were not looking at before. So it's a much more simpler version of singular value decomposition. Your U and V at this point, when your matrix itself is symmetric, it's not going to be U and V. It's not going to be two separate matrices, but rather it's going to be the same matrix that is there twice. Your U will be equal to V, and those things we're going to call as eigenvectors. And our singular values that we had called before are going to be the eigenvalues. So your Hessian matrix, the good thing about it is that it's always a symmetric matrix. So there's positive definite symmetric matrix. And whenever we do singular value decomposition on it, we call the outputs, the vectors themselves, as the eigenvectors and eigenvalues. And we can use this in order to characterize the curvature. So if you have this kind of a very large footprint of your loss, then we call that as low curvature. If there's a high curvature, essentially means that there is more changes. This is hard. I don't know how visible or how easy it is to understand this image. You need to look at this from the top-down framework. Right now, we are looking at it from sideways, but if you were to look at it from a top-down framework, this is an oval, essentially, where the low curvature is basically the largest radius over here, and the smaller one is the higher curvature. So it basically reduces very quickly. That is essentially what curvature means, how fast it reduces across the parameter space. The way we would characterize it based on numbers is this idea of condition number. It's the ratio of the largest and smallest eigenvalue of your Hessian matrix. That gives you the idea of a condition number. Essentially, if your condition number is, let's say, very high, that means your largest eigenvalue is very, very high compared to your lowest eigenvalue, then we have a problem. Then this means that your network has only trained a single dimension, so it has only trained across one dimension rather than both dimensions, and it's doing well in one of the dimensions, but it's not using the other dimension at all. Or in other words, it's not using some of the neurons while it's using the other neurons, which is bad, which means that you are using a lot of space in order to construct your network, but it's really not helping you in terms of actually doing the learning portion. So it's a good way of thinking about how to characterize my loss manifold or my loss surface. Any questions in the condition number and eigenvalues, eigenvectors? Yes? Regularization is your best bet. That basically means that one of your dimensions, W, is not learning as well, right? So by having something like a L2 normalization, or L2 like regularization, you're making sure that one of your W is not very high compared to the other ones. L2 regularization essentially takes the square of your W's and uses it within the loss function. This means that one of your W's will not become high. Otherwise, your loss is going to be very high. So all your W's will be in a similar state, I would say, or will have a similar number of or similar amount of values. So regularization is your best bet. Feature is what? Feature is irrelevant. It could be, but again, when we talk about a million different images, we are doing auto extraction of features, right? So the network itself is extracting these features and then working on top of it. So essentially, when something feature is irrelevant, that would mean that that part of the network is irrelevant. The extraction part of that network is irrelevant. So again, you're back to the same condition number, where that means that you should change the way your weights are in order to extract it. So that means it's good to have regularization again within that framework. All right, then we move on to the idea of adaptive learning. So I have quite a few slides on the adaptive learning itself, but again, the math portion is not as important here. We are more interested in the intuition for everything. So the first adaptive gradient method we are going to see is AdaGrad, adaptive gradients. The idea is that it's accumulated over time. So momentum was just looking at the previous iteration, the gradient from the previous iteration in order to update it. But then now adaptive gradient accumulates these gradients over time, and it's basically a square of your gradients. So where's my cursor? Yes, dou L by dou W whole square. And the way it's used is also different. Before, what you saw in momentum was that this momentum it basically multiplies alpha, right? But in AdaGrad, this accumulated gradient essentially changes your alpha. So in other words, what is happening is, before, when I mentioned 200 epochs, the first 60 will be 0.1, 0.01. This is something we start off with. We in the coding itself, we make this kind of an assumption that this is how we do it. But instead of that, if you want to have more of an adaptive framework for changing your learning rate, you'll use something like AdaGrad, where your alpha is now dependent on all the previous gradients. And this can be used in order to change your learning rate across different epochs. As you go across epochs, right, your G function is going to increase or decrease depending on how your gradients are changing. If not much change is happening, then your AdaGrad will increase the alpha. If there is a lot of changes, then your AdaGrad will decrease the alpha, and so on. So it's an adaptive way of thinking about how learning rate changes across your training framework. Also, it's like an element-wise scaling of the gradient. So you'll have dou W1 will be different from dou W2 and so on. So it gives you this kind of a per weight or a per dimension kind of scaling as well, which helps in that loss surface and loss scaling as well, right? Because you don't want one W to have a high curvature versus the other W to have a low curvature. So this helps you in that fashion as well. So directions with high curvature have larger gradients, and learning rate reduces for damped update, essentially. So it helps you damping that particular W or that parameter. So this is kind of a demo for, let's say, something like gradient descent versus AdaGrad. So whenever you have something like a saddle point, you will be able to change your alpha in order to get to a certain stage, which is your output. AdaGrad here is in white versus gradient descent is in cyan. The learning rate of AdaGrad is set to be higher than that of gradient descent, but the point that AdaGrad's path is straighter stays largely true regardless of your learning rate, because learning rate is something that is adapted across your epochs and iterations rather than something that you define in the beginning itself. Next adaptive learning strategy we'll look at is RMS prop. So this is root mean square propagation. By the way, so I'm just talking about all these things as if they're simple math equations. They're not. They're classes by themselves. And if you go on to PyTorch, for instance, all of this is just a single line of code. You can define your optimizer to be something like stochastic gradient descent, SGD, or RMS prop, or AdaGrad, or with momentum is nothing more than a simple argument that you pass into your optimization framework, and so on. So it's in terms of coding, it is very straightforward. You don't really have to do all the coding yourself. So what is RMS prop? The difference here from AdaGrad is that there's a beta parameter that is added here. Instead of using the accumulated gradients directly themselves, you are quantifying it by adding a beta parameter on top of these weighted average of squared gradients. That's the only difference. There's a beta, and then there's a 1 minus beta to account for that beta in your gradient framework. The way you adapt your W is still the same. The way you add RMS prop onto alpha is still going to be the same. Now, the reason we need this is because in the beginning portion of your training, gradients are going to be very, very, very high. If you've actually seen during the training process, your gradients, even with very simple data sets, the gradients themselves are very high. So AdaGrad can become very slow. If your gradients are very high, then that means alpha divided by something is of something very big is going to be very low, right? So that means that AdaGrad will make your function, your optimization framework extremely slow in the beginning. It won't move at all, and the alphas will be very, very less. So you don't want that to happen. So that's why you have RMS prop. It solves this by adding beta, which we call a decay parameter. Decay rate is saying that only recent gradients are more important. in your framework, optimization framework, rather than all the previous gradients that had existed. So this is kind of like a demo. The white is Adagrad versus the green is the RMS prop that we are seeing now. So what you'll notice is that after a certain while, your Adagrad stops in the training procedure or optimization. It's because your sum of gradients is now so high that WT plus 1 equals WT minus alpha is it's 0. Alpha divided by a very high number, it's going to be 0. So it's not moving at all. Nothing is happening. But if you now have RMS prop, the size of these squares, by the way, is the size of the square of gradients in different dimensions. You have 2 dimensions here. So the sum of square of those gradients are the squares that you see. As you can see, RMS prop, something exists and it's able to come near the center, which is the global minima, versus something like Adagrad is not able to. Yes, question. Mm-hmm. But you already, so the first iteration, let's say, has about 1,000, this thing, right? And the next iteration, the gradients are very low, as you say. It could be 0.1. But now you're doing a 1,000 plus 0.1, so it's still 1,000.1. So it's still very high in Adagrad. So it's not able to fix itself. But if you have a decay parameter like beta, and you say that the first time it's like 0.9, then after 10 iterations, the effect of 1,000 has now reduced to something like 100. So your 0.1 right now is going to matter, and it's going to be used within the framework. It's the initial part that is very hard for Adagrad to take care of. After a certain while, it does quite well. But to overcome that initial part, that's why we need this kind of a decay rate within RMS Pro. All right, I think we're out of time, 10:45. There's a few more slides here which we'll cover on Monday.